Good evening, ladies and gentlemen, and welcome to the SAIEE Railway Chapter webinar. We will be discussing tonight fuel cell rail motive power applications. Before we start, a few webinar considerations. Attendees are reminded to ensure the volume is turned up on their device. Ensure you have a stable internet connection. This will ensure the streaming and audio will run smoothly. Attendees can ask questions via the questions panel located within the GoToWebinar control panel. By default, the control panel is located on the right-hand side of your screen. The chat function is reserved for webinar organizers and panelists to communicate with attendees. Attendees will not be able to chat each other. However, we encourage you to ask questions. A recording of this webinar will be made available on the SAIEE TV channel on YouTube. You will find the link, the registration link in the chat box. Please register, it is free. This recording of this webinar will be uploaded under the Railway Chapter playlist. A certificate of attendance will be issued a few weeks after this webinar, once we have received the CPD validation number from EXA. I'd like to introduce you now tonight to our host, Mr. Xolani Tshwane, who's the Secretary of the SAIEE Railway Chapter. Xolani obtained a bachelor's degree in electrical engineering from the University of KwaZulu-Natal and is currently enrolled for a master's degree in engineering management at the University of Pretoria. He has over 5 years of experience working as an engineer in Transnet's research and development space. He is currently serving as the Secretary of the SAIEE Railway Chapter. Over to you, Xolani.
Thank you. Thank you, Mix, for that introduction. If you can just display Mr. Chitene's slide. Thanks once again, and also to the attendees. Welcome to this webinar. Our panelist today is Mr. Chitene. Mr. Chitene is a certified project management professional with Project Management Institute and a registered professional construction project manager with the SACP CMP. Besides an enduring passion for the railway, his primary professional interests include hydrogen fuel cell, power electronics, electric drive technology, and the renewable energy. He currently serves as the CEO of Puma Holdings and engineering and project management services consultant for the built environment. Mr. Chitene, thanks for being our presenter today for the webinar. You may take control of the webinar.
Good evening, everybody, and thank you for spending some of your precious time to listen to this short webinar on motive power applications, for fuel cells in the railway industry. I believe I'm audible and I can proceed.
Yes, you can, sir.
Thank you. Thank you for the kind introduction, Mr. Zwane. I will delve right into my presentation. Let me just make sure that I have total control of, yes. So basically, my presentation will go through a brief introduction, a short history of rail traction. Obviously, during this short time that we have, it's not possible for us to get into a lot of detail. So it will be pretty fast. We'll then just delve into the basic operations of fuel cells, fuel cell technology, and then consider in a little bit more detail how they can be and how they are already being applied, in the railway industry. And then lastly, we'll look at the opportunities for the South African rail industry. So the situation we find ourselves in as human beings is that our advancement, as we have advanced our civilization, that has come at great cost to the environment. The degradation to the environment wasn't really deliberate, but a lot of the circumstances were unforeseen. For instance, when the steam engine was first discovered, and the steam locomotive came into being, when we started building large coal-fired power stations, we were not really aware at that time of the negative consequences to the environment. But these are things that have come to, if you like, haunt us later on. And railways, being a part of the improvement in the civilization, have also come at great cost. And that's why we have, we have progressed from steam locomotives to diesel electric locomotives to electric locomotives. And at the present moment, we're now looking at making railways cleaner and greener, and less polluting to the environment. The unfortunate place we find ourselves in right now is, I believe, that we are part of that cohort of humanity that is tasked with doing something now, something tangible for the environment. Otherwise, we'll lose it completely for future generations. So basically, this presentation is a short look at how railways can become less polluting. What's already happening, within the railway industry worldwide, and like I said, how South Africa can also become part of that revolution. So, if you look at the history of rail traction, we have come from animal-hauled railways back in the 6th century in Greece. Modern railways really developed as a result of the invention of the steam engine, leading to the steam locomotives in the early 19th century, especially in Britain. What happened then was that the railways reduced the cost of doing business, cost of shipping and communication, and the economic benefits to society were actually huge. But as a result of some of the inefficiencies that we'll get into a little bit more, we needed to improve. And so railways became electrified. We started using diesel electric locomotives to the extent that right now, worldwide, probably the largest source of motive power, rail motive power, is diesel electric locomotives. But because obviously of the pollution problems that we face as humanity, there is now a drive to electrify railways, as well as to see even how the electrified railways themselves can become, less polluting. Like I said, the first real mover for railways was steam locomotives, and the operation and the technology was simple and basic. Coal being the fuel source, you use a boiler to heat up water, and you use steam basically as the source of your motive power. These steam locomotives became prevalent in Britain during the 19th century. And they were used in the railway industry for quite a bit of the 20th century until about mid-20th century. Like I alluded to earlier, the major drawbacks is the limited efficiency, as well as the huge environmental problem that we get from using steam locomotives. If you look at what's on the screen right now, is a typical steam locomotive. That was the characteristics of a typical steam locomotive. When you look down here, the overall efficiency was basically up to a maximum of about 10%, with a huge emissions problem. Sulfur dioxide, carbon dioxide, nitrates, particulates, and heavy metals. And as a result of especially these two issues, that is the inefficiency of the motive power source as well as the huge emissions problems, the steam locomotive was gradually phased out to the extent that now very few railways worldwide use them. You can still jump onto some tourist trains or vacation trains that are being run on steam locomotives, but is a commercial source of motive power. Steam locomotives have largely been phased out. Then we basically moved on to diesel electric locomotives. And essentially what happens in a diesel electric locomotive is we take an internal combustion engine running on diesel fuel. We use that to generate electricity on board the locomotive. And then early locomotives used to have DC generators. Then, we had alternator rectifier combinations, but basically these were used to drive DC traction motors initially, and then with the advancement of technology and improvements in AC drives, we then tended to use AC drives for these locomotives. The main advantage over the steam locomotives was the improvement in efficiency, which came about basically as a replacement of the mechanical drive train by using electric transmission. So there is no direct mechanical coupling between the power source and the traction motors. And this resulted in a huge improvement as far as efficiency was concerned. Unfortunately, we still remained encumbered with the emissions problems, carbon monoxide, carbon dioxide, nitrates, as well as the particulates. However, the majority of locomotives that are still in use today are diesel electric locomotives. But if we move a little bit forward, we then have electric locomotives. And what happened here was we replaced the onboard generation of electricity on the locomotives by sourcing the electrical power from an external source, i.e. from the national grid via the pantograph on the locomotive. What this then does is it improved vastly the efficiency of the locomotive, and that is if we ignore the source of the electrical power that we are utilizing. So we don't have a diesel engine, we don't have a generator on board, we have the bulk power components are static components which are efficient. And what happened was we had a huge increase in motive power as well as a huge increase in efficiency. And if we ignore the fact that this electricity is being generated somewhere else, then we also don't have negative harmful emissions from the locomotive. So very little emissions produced, much less maintenance when you compare it with the diesel electric locomotive. And the trend nowadays is for most railways to actually electrify. Of course, the main issue that comes with using electric locomotives is that you need the supply infrastructure, i.e. your overhead catenary systems or HTE, which is our local nomenclature here, and that also then increases the cost of running electrified railways. But from the emissions point of view, from the pollution point of view, there is a vast improvement when you compare to diesel electric locomotives. So basically, quickly running through the environmental considerations, I'm saying here that advancement has come at great cost. The rail transport, although it has improved the lives of people, it's had a negative impact on the environment. Steam locomotives were extremely inefficient. Diesel electric locomotives gave us a vast improvement as far as efficiency is concerned over steam, but again, we still remained encumbered with the emissions problems. Electric locomotives are non-polluting at the point of use, i.e. when the locomotive is on the track, drawing power from its pantograph and pulling the train, we can consider it non-polluting there. But for us to be holistic and actually fair, we need to consider where that electrical power is coming from. In our country, in South Africa, the bulk of that power is coming from a coal-fired power station. And so from an environmental point of view, we must then include the efficiency of our coal-fired power stations. And then if we do that, you'll then find that the efficiency, the real life efficiency of the electric locomotives drops from 90 to 95% to somewhere around between 30 and 40%. And then also when we say it's got zero emissions, when we include the emissions of the power source, then we realize that it really is not that clean after all. So if you look at the last bullet point there, I'm saying for the electric locomotive to be considered truly environmentally friendly, cleaner sources of primary electrical power have to be utilized. That those cleaner sources of primary electrical power could be batteries. There are locomotives that are in trial right now that are running on lithium batteries. It could be fuel cells, or it would mean then that we are generating this electricity from renewable sources like solar or wind or geothermal, depending on wherever we are in the world. Fuel cells. What I realized is, it's a very interesting branch of chemistry or electrical engineering, and we really will not have much time to delve into fuel cells, but they can be traced back to 1839. And basically, in its basic form, let me move from this slide. These slides will be available for anyone who would want them. If I can basically go to the next slide. The fuel cell basically uses hydrogen and oxygen as the anode and the cathode. And in this, it is in this respect that it is different from the battery, because in the standard battery, the anode and the cathode basically part of the construction, and they are consumed during the operation of the battery. Obviously, if it's a rechargeable battery, we can restore them. But in a fuel cell, the major difference is that the anode and the cathode are consumables. So depending on the supply of the hydrogen or the oxygen, which basically is usually depending on the type of fuel cell, basically the operation of the fuel cell is not really dependent on anything. Nothing needs to be replenished as long as you've got sufficient hydrogen and sufficient oxygen to supply the fuel cell. So what I'm going to do here is basically go through quickly the different type of fuel cells. I think we can find this in the literature, and we don't have enough time to dwell a lot on the fuel cell itself. One of the more commercial types of fuel cells is the alkaline fuel cell. It operates on compressed hydrogen and oxygen and an aqueous solution, usually of potassium hydroxide, as the electrolyte. The operating temperature is relatively on the low side, between 150 and 200 degrees. And then there's a bit of a description on the actual transport mechanism within the cell itself. But I think the important thing is that commercial units of up to around 200 kilowatts are in current production right now as we speak. And then in the next slide, I discuss the advantages and disadvantages of alkaline fuel cells. They operate at low temperatures, they fast startup times, a very high efficiency up to 70%. They need little or no expensive platinum catalyst. Platinum, depending on the type of fuel cell that is being used, can be a very high cost component in the construction of the fuel cell. On the disadvantaged side, you know, they have an extreme intolerance to carbon dioxide, and the fact that the electrolyte that is being used is a liquid introduces handling problems. There are also water management problems within the cell itself, and it's got a relatively short lifetime. But they are in commercial use, they are in commercial operation, and there is an example of an alkaline fuel cell powering a telecoms equipment somewhere in the Scandinavian part of the world. The next major fuel cell type is the molten carbonate fuel cells. These use carbonates as salts. These salts are heated to quite a high temperature, where the salt melts and conducts carbonate ions from the cathode to the anode. Then again, we go through the transport mechanisms. Demonstration units have been produced up to 2 megawatts. So that's quite a fast improvement from the alkaline fuel cell, and designs exist for units of up to 100 megawatts. The advantage is that they support internal reforming of the hydrocarbon fuels. They also generate a high-grade waste heat, and this can be very useful in a combined heat and power applications. And it therefore actually makes molten carbonate fuel cells very useful and very suitable for stationary applications. Fast reaction kinetics efficiency is also relatively high. I think on the disadvantages side, corrosion becomes a major problem, and they are also highly intolerant to sulfur. We still have the same problem of a liquid electrolyte that introduces handling problems, and molten carbonate fuel cells unfortunately require considerable warm-up period. That's because you've got to heat the carbonate until it melts in order for the cell to start functioning properly. But again, they are actually in commercial production right now, and that's an example of a 1.4 megawatt natural gas-fed molten carbonate fuel cell somewhere in the United States. Natural gas in the sense that the hydrogen that the fuel cell requires is not fed into the cell as pure hydrogen, but as natural gas, which is reformed to produce the hydrogen that's required. The next major type of fuel cell is the phosphoric acid fuel cell. Again, this one operates at relatively low temperatures. It uses phosphoric acid within a silicon carbide matrix as the electrolyte. Again, we go through the transport mechanisms. The efficiency of this cell is basically up to a maximum of around 50%. But if the waste heat that is produced in the cell is used to regenerate electricity, then you can increase that efficiency to around 90%. It's best suited for stationary applications, and units up to 11 megawatts have been tested. The major advantage is that the phosphoric acid fuel cell is highly tolerant to carbon dioxide. So as a result of that, you can actually use unscrubbed air as the oxidant and reformate as fuel. It operates at low temperatures, as we saw, and it's also got a stable electrolyte characteristics. On the disadvantages side, we have low carbon monoxide tolerance. It uses a corrosive liquid as electrolyte, and then that becomes problematic as far as the handling is concerned. It also allows product water to enter and dilute the electrolyte. The phosphoric acid fuel cells tend to be large and heavy, and they can't auto-reform. also they must be warmed up before operation. In other words, it becomes low or very slow startup. But again, they are in commercial production, and that's an example of a 105 kilowatt phosphoric acid fuel cell powered by natural gas. The next type is the proton exchange fuel cell, the PEM fuel cell. And this is probably one of the more popular ones, especially when it comes to transportation applications. Toyota has got a vehicle. I haven't seen one in South Africa, but there are quite a few examples worldwide. The Mirai, the Toyota Mirai, which is a hydrogen-fueled car, it actually uses PEM fuel cells. Basically, these work with a polymer electrolyte in the form of a thin membrane. The membrane is small, it's light, and it works at low temperatures, which is an advantage. Unfortunately, this particular fuel cell requires a platinum catalyst on both sides of the membrane. And then we go through the transport mechanism within the cell itself. Efficiency is in the region of 50%. If you are to use this with any other source that is not pure hydrogen, then you need a reformer, to use other fuels, like methanol or natural gas or whatever. Automotive applications, like I alluded to earlier with Toyota, have fueled a lot of the research around PEM fuel cells. Demonstration units of 50 kilowatts and higher now are actually being produced, and as much as half a megawatt, are under development right now. The advantages of PEM fuel cells: they are carbon dioxide tolerant, they operate at low temperature and pressure, and this simplifies the materials that we need to use, and it also provides for quick startup. They use a solid electrolyte, and so the issues of handling liquids become less of an issue. They use a non-corrosive electrolyte. Pure water operation minimizes corrosion problems and improves safety. On the disadvantage side, we still have the low tolerance to sulfur compounds. It needs reactant gas humidification. This can be energy intensive and then increases the system complexity, which then has the tendency of reducing the efficiency, the overall efficiency of the system. And like I alluded to earlier, unfortunately, it requires the use of the platinum catalyst. I think that's one of the things that we have to trade off for the low temperatures and ease of operation of this fuel cell. And the use of the expensive membrane that is difficult to work with, can be an issue. But manufacturing, the way manufacturing is right now, it's actually becoming a very mature kind of fuel cell, and some of these things are becoming less and less of issues. That's an example of a fuel cell stack from Horizon Fuel Cell Technologies. And like I said, the transportation industry, being cars as well as buses, have actually driven the development of PEM fuel cells. And this is an example of a hydrogen fuel cell bus, electric bus. And a lot of these buses running on hydrogen fuel cells are actually in use right now in Europe and in North America, and hopefully one of these days we will see them on the roads, Ria Vaya here in Johannesburg and my city bus in Cape Town. The last fuel cell type that I'll talk about now is the solid oxide fuel cell. This uses a hard ceramic electrolyte and operates at very high temperatures, up to about 1,000 degrees Celsius. A mixture of zirconium oxide and calcium oxide forms crystal lattice, though other oxide combinations, can be used. The solid electrolyte is coated on both sides with specialized porous electrode materials. These can be tubular, as shown in this diagram, or they can also be planar. And then we go through the designs and the transportation. The generating efficiencies of the solid oxide fuel cells are actually up to 60%, and they are best suited for stationary applications. Demonstration units, up to 100 megawatts are under development. What I find a little bit exciting about solid oxide fuel cells is I believe that there is a company already in South Africa that is embarked on the manufacture of these fuel cells, and I see a lot of opportunity, for these fuel cells, especially the solid oxide fuel cells, in terms of storage and in terms of being coupled to some of the renewables, the renewable energy sources that we have, to make the power that's being generated there more dispatchable. So we then go through the advantages and disadvantages of solid oxide fuel cells, and the major disadvantage is obviously the very high operating temperature, and that's why they are really that suited for stationary applications. Again, they are in commercial applications, and that's an example of a 4.75 megawatt solid oxide fuel cell installation in California in the United States. Now, I think this slide is very interesting in the sense that it's basically comparing power sources which are applicable to the rail industry. And basically here we are looking at fuel cells, we're looking at the internal combustion engine. And if you look at diesel electric internal combustion engines, it's in the sort of mid-power, mid-efficiency range. By far, the greatest amount of power being generated is by steam and gas turbines. We can generate huge amounts of power from these, but the efficiency again tends to be on the low side. If you look at fuel cells, the power bandwidth, because of the developments that are coming up, is quite high, and they represent the most efficient type of generation, as it were. I think I need to be moving much faster than I am. And then on the side there, there's a slide on the energy conversion, and then that's comparing the fuel cells, the battery, as well as the internal combustion engine. I think I'll skip that. Basically, that's a comparison of the fuel cell technologies that we've already gone through. So the advantages of fuel cell systems, basically, it gives us the opportunity to generate electricity with little or no pollution. I must emphasize here that it's zero pollution if we're running it only on pure hydrogen. But then again, the question comes, how was that a pure hydrogen sourced? So if our hydrogen has been manufactured through the electrolysis way, using renewable electricity, i.e. electricity generated from solar or wind or other renewable sources, then we can consider the fuel cell pollution-free. But at the moment, the bulk of the hydrogen that's commercially on sale is what you could call either gray or blue. And what that means is that, the hydrogen fuel cell will only be pollution-free at source. But, when you consider the overall environmental impact, then it's not that completely pollution-free. Again, there are a lot of there are some disadvantages which relate to manufacture, which also relate to storage. A lot of these disadvantages, you know, we are finding ways around, to the extent now that we can actually utilize fuel cell systems in a safe and environmentally friendly way. Again, that's another slide that basically compares the fuel cell to the battery, to the internal combustion engine. Now, I think we come a little bit more directly to the rail motive power environment. I think on the left there is the typical torque speed characteristic of the locomotive. We've got the constant tractive effort part, where we need the locomotive to move from rest up to the desired speed. And then we've got the constant power line, basically as the locomotive or the train or the traction motor, because this is really a reflection of the traction motor itself when it moves up to its maximum design speed. So as far as the power source is concerned, the power source, whether it be a steam locomotive, i.e. coal firing a furnace, you know, which heats up a boiler to give us steam, or whether it's the diesel engine, the diesel fuel in the diesel engine, or electricity. What is required is for the power to be available to the locomotive or to the train at every part, you know, of its journey. In other words, the instantaneous power output of the locomotive or of the source must always match the instantaneous power demanded by the load as the load is changing. And also, it is important that the power unit operate in its optimal or safe operating region, you know, throughout. When you look at locomotives, besides the power source itself, you then have gearing, and you've got different types of gearing depending on whether you're running a freight train. You gear a freight train more towards gearing for locomotives is more towards higher tractive effort at the expense of top speed, whereas for passenger applications, you want a little bit more speed, and you gear it accordingly. So why should we consider fuel cells in the rail environment? I think the main focus for transportation up until now, and now I mean maybe 5 or so years ago, has been on trucks, on buses, and on cars. But the research on rail transportation has lagged behind. However, we are no longer that far behind as far as the rail environment is concerned. In 2019, Alstom revealed plans for a pilot project, you know, for a passenger train. And although the motive power for rail applications is determined by many factors, you know, the environment in terms of efficiency, the environment in terms of pollution must right now and going forward become a major consideration in everything that we do. When you consider fuel sources, this slide shows that outside of uranium, hydrogen is one of the highest, is the highest specific, it has got the highest specific energy outside uranium that we have. And it would obviously then be good if we can utilize that that energy and that efficiency. I think I'll skip a little bit for time reasons. I think one of the issues that comes up always when it comes to hydrogen is safety. How safe is it? But there are a lot of things that go for hydrogen. It's not toxic. A leak will not contaminate the environment, even if it leaks. It's very light, and so when it leaks, it rapidly rises to the upper parts of the atmosphere. It is highly flammable, but it's been produced and stored and transported very safely for more than 50 years. It also has a much lower radiant heat capacity than conventional fossil fuels. And there was a study, or there was a study, an exercise, an experiment actually done by the University of Miami, and it shows here the effects of a petrol car burning up, basically, as opposed to a hydrogen-powered car burning up. And you can see that the petrol car was virtually destroyed, whilst the hydrogen car remains clean. So hydrogen is not as unsafe as, you know, the reputation it has. It's a product, it's a gas that we've handled very much in the past, and we know how to handle. When you compare an electric locomotive versus a fuel cell locomotive, so the electric locomotive utilizes external power. The fuel cell locomotive, just like the diesel electric locomotive, generates its own power. The result of that is that the electric locomotive requires an extensive external infrastructure in the form of OCS equipment, as well as the utility grid, which the fuel cell locomotive does not need. The electric locomotive is extremely efficient if you don't consider how the power is being generated. Whereas when you compare apples with apples, it's generally true that the fuel cell locomotive will actually be more efficient than the diesel electric locomotive, unless, of course, you are accessing the electricity from an extremely efficient source. The electric locomotive is zero harmful emissions only at the point of source. We've discussed that before. Again, the fuel cell locomotive will have zero harmful emissions at the point of source, depending on how the hydrogen has been sourced. So what I then did was I took a typical Transnet locomotive, class 39200, and looked at some of its energy requirements. So if you look at this locomotive, it has got a diesel tank with a 7,400 liters capacity. What that means is that, and that's the locomotive. Those are some of the curves. But what that means, we'll dwell on this a little bit, is if you look at that locomotive, it stores 7,400 liters of diesel. Basically, what that means is that if you look at the graphs and the curves, it's storing a total amount of energy, which is 270,899 megajoules. Now, if we wanted to have the same locomotive with the same energy capacity, but utilizing hydrogen as a fuel source, basically what that translates to is you would need 50 cubic meter tank of hydrogen, which basically gives you the same amount of energy, and that's roughly, you know, coming from about 2,000 kilograms of hydrogen that is pressurized at 700 bar. And they you know, graphs, you know, on hydrogen storage. We can use this to determine, you know, how you store hydrogen. If you look at this graph, basically 2 is the region that I'm playing in. That's around 20 degrees Celsius, 293 Kelvin, whereas 3 is the cryogenic sort of range. So what this shows is that it is possible to take a locomotive like the class 39200 from Transnet and essentially retool, refit, and run it on hydrogen as a fuel source using hydrogen fuel cells. So what that means is you'd start with an existing locomotive, you'd remove the diesel engine, the alternator and the rectifier combination, remove the diesel tank and everything that is associated with that power source, and then you would replace it with hydrogen fuel cell, the hydrogen storage. You'd also need lithium batteries for starting ETC. The hydrogen fuel cell and the lithium battery obviously would then have to be correctly sized and specified to suit the traction motors, to suit the locomotive control systems, the auxiliaries, etc. Appropriate hydrogen storage and fueling facilities would then have to be established. You know, if, for instance, Transnet or PRASA decided to have a pilot route, that then would have to be established. And obviously, new practices, safety standards, codes of practice would have to be written and developed. Maybe they are already there, I'm not very sure. But just to show that what I am talking about is not really a pie in the sky, it's already been done. There's an example here from Canadian Pacific Rail, where they took basically a locomotive that is very similar to the Transnet Class 39 that I was talking about. They took this as a pilot project. It's being run by Canadian Pacific as part of their sustainability commitment. In fact, they received honorable mention at COP26. I think it was last year in Scotland. They have currently around 400 million rands committed. The locomotive was demonstrated last year, actually in September. And like I said, it's a conversion of an existing General Motors diesel locomotive. It utilizes Ballard PEM fuel cells, hydrogen fuel cells and batteries. And it's going to use green hydrogen from Canadian Pacific's own solar-powered electrolysis. So they wanted to make sure that the hydrogen is pure. So they are generating the hydrogen using electrolysis that is being powered by solar power. And they have plans to convert some of their shunting locomotives. Obviously, this particular one is a mainline locomotive, and trials are underway right now. Another example is a similar locomotive, a little bit smaller, but built by CRRC Datong in China. The locomotive is in service in Inner Mongolia. It utilizes hydrogen fuel cells and lithium batteries again, and it's got a total output of 700 kilowatts, maximum design speed of 80 kilometers per hour. The only thing that I found rather an irony as far as this locomotive is concerned is on the line that it's being used to transport mainly coal. So we are using a very environmentally friendly hydrogen fuel cell, locomotive to transport coal. Again, this is an example of a shunting locomotive by Sierra Northern Rail in the US, and basically it shows the steps of removing the diesel engine and associated equipment, replacing it with hydrogen fuel cells, with hydrogen storage, again lithium batteries, and the finished locomotive, which is actually in shunting service right now. So basically what this shows is that from a freight rail point of view, it is possible to actually convert existing diesel electric locomotives to run them on hydrogen fuel cells. I alluded to earlier about the Hearthstone Train. This is the Coradia Island, developed by the German government as part of their innovation program. It was first unveiled in 2016, and the initial test runs were in March 2017. This particular train uses a low-flow passenger train, and the PEM fuel cells are actually located on the roof. And then the lithium batteries and the power converters are fitted under the floor. Again, the trials are already underway. The beauty about this, as you can see here, is we don't need any overhead catenary infrastructure to power the train, which is essentially a zero emission train. There's another passenger example. This was the first hydrogen powered train in the UK. It was demonstrated in June 2019. It's based again on an existing train set, and this was a collaboration between the University of Birmingham and Porterbrook. Porterbrook is a rail operator in the UK. It uses just under 300 kilograms of hydrogen stored on board in 36 high pressure tanks, and again it uses PEM hydrogen fuel cells, which utilize pure hydrogen. And the oxygen that's required is sourced directly from the air. So basically, what this shows is that hydrogen fuel cell trains or motive power is possible both in the freight as well as the passenger, environment. So if we look at the rail market, the South African rail environment now, and now I'm coming to a close. I think we have the most advanced rail network in Africa, possibly, definitely in sub-Saharan Africa, although it's got a lot of its problems, a lot of which has been due to underdevelopment, underinvestment, and a whole host of other issues. But the government has been crying for private sector participation. Obviously, the policies have to be in place, to allow for meaningful private sector participation. But I do believe that the government is serious about it, and it will happen. And I think it will be a good thing, as the private sector becomes more and more involved in the South African rail market, that we come in with newer technologies, like fuel cell, locomotives to reduce the impact on the environment. I think in the next slide, I've got, we have a particular problem as far as South Africa is concerned, and that's the problem of copper theft. This theft targets the power, rail, and telecom sectors, i.e. Eskom, Transnet, PRASA, and telecoms. And, when I was doing the research, I think on an annual basis, the country loses more than 10 billion rands to the theft. In fact, last year, I think Transnet Freight Rail reported a loss of more than 1,000 kilometers of cable between January and October last year. And again, from the press, there's actually news that Transnet is reconsidering de-electrifying some of the routes and running diesel-electric trains. I think that this presents an opportunity, for then introducing hydrogen fuel cell powered, trains in these areas where Transnet feels, they can't continue running electric trains because of the thefts, but instead of reverting to diesel electric trains, then we could use hydrogen fuel powered trains. PRASA pretty much faces the same problem as Transnet Freight Rail. So I'm saying here that there's an opportunity to run hydrogen fuel trains if they're available, and this makes it then more urgent for us as a country to dig deeper into research, into development of these things, because as far as we are concerned as a country, I think we've got enough research and development facilities, as well as manufacturing facilities within South Africa, for us to be able to, become at par with the rest of the world, and maybe even lead, in other things. And if you look at this whole thing, what it will lead us into is, the development of hydrogen, green hydrogen, as we move from gray and blue hydrogen to green hydrogen itself, power electronics, the fuel cells themselves. I think South Africa, if I'm not mistaken, it is the largest producer of platinum. And platinum is one of the major components of especially PEM hydrogen fuel cells, and there's no reason why we cannot become a leader in that field. Same thing with manufacturing. As far as the railways is concerned, South Africa actually is a very good base for rail engineering, both within Transnet itself as well as within some of the other private companies that used to support the rail industry. I think what we need to do is to resuscitate that, and as we resuscitate that, we then get ahead of the curve in terms of the technology, and that can become a very, very good platform, you know, for us to advance, not just advance, but to critically create jobs at every level, you know, at the high level in terms of R&D, as well as at the manufacturing level, and even at the operating level. Because I think one of the things that the rail industry wants to do within the country, as well as within the region, is to move freight, especially away from the roads and back onto the rail. And I think we can do that as we make the railways more efficient and more environmentally friendly. I think with that, I'm pretty much coming to an end. This basically says there's a whole hydrogen economy. There's been a lot of talk around the hydrogen economy, both from the supply side as well as from the utilization side. And the rail transport can become a very good, you know, enabler, you know, as far as the utilization side of the hydrogen economy is concerned, especially by going hydrogen fuel cell motive power, both on the freight side as well as on the passenger side. The next steps, and this is my last slide, I just took some quotes from Shakespeare that we need to do things. And I think doing things basically means government, the private sector, as well as all the other players in the industry, especially the state-owned companies, of which Transnet and PRASA are an integral part, you know, coming together and deciding that, you know what, there's things that need to be done, which makes sense both from the commercial and from the environmental side of things, and let's get together and let's do what needs to be done. Thank you.
Thank you very much, Mr. Chitele, for this insightful presentation. To the attendees, if you've got any questions that you would like to pose to Mr. Chitele, may you either put them in the chat or you can raise your hand, and then we'll unmute you, and then you can ask the question. All right, I think we've got the question already. Mr. Chitele, are you able to view the question?
Kolani, sorry, Kenneth. Kolani, Mr. Chitele cannot view the questions. You can just ask him the questions. You can both please switch on your webcams, and then we can just view the questions. We encourage our attendees to please ask questions, which we'll be dealing with now. Thank you.
All right, thank you, Means. Okay, so the first question is from Dr. Naidu. So Dr. Naidu is saying, thank you. An excellent summary over time with good emphasis on efficiency of energy conversion. PEM and SOFC offer great opportunities for South Africa. Platinum beneficiation and hydrogen, a move from grey to green as energy carrier. Thank you, and we invite you to UJ. We have an advanced PEM SOFC lab. There's a project converting existing liquid fuels vehicles to electric vehicles. So he says the students at UJ can learn from the lessons as rail moved from steam to diesel to electric drive. Yeah, let us build a fuel cell powered rail electric drive using simulations. We can demonstrate same to the leadership and go to the next step of converting existing diesel and electric traction to electric or to fuel cell. We need lots of jobs. Together we can deliver a better quality of life to all. Well done and thank you. That's Dr. Pet Naidu, who is a member of the South African Institute of Electrical Engineers and Railway Chapter member as well.
That is actually music.
You can, yes.
Sorry, Mrs. Wane, I was actually saying that is actually music to my ears. I think that is the kind of collaboration that we need, you know, from the private sector, from academia, as well as from government and state-owned enterprises. I think many times we forget that that is how the capability that we have today within the country actually developed. And we've kind of slackened, I believe, but we need to get back to doing that and doing it, you know, vigorously. So I definitely will take up that invitation and I'll pay UJ a visit.
Right. Thank you, Mr. Chitene, for that. There's another question from Timothy Kamikel. So he's asking, are there any conversion of trains that are planned in South Africa currently?
Not as far as I know, but maybe you can assist me, Mr. Zwane. What I know is that this is something that Transnet has been looking into, but I'm not quite sure where the progress is.
All right. So on my side, as far as I know, on Transnet side, there hasn't been any freight train or freight locomotive that has been planned for any conversion. However, there is currently research and development work that is being done on that space on the Transnet side. And it may just only be limited to shunting locomotives for now. But yeah, that's in the pipeline. So those are the two questions that I have for now. So on my side, Timothy, I've got a question. Not Timothy, apologies, Mr. Chitene. What is, from your research thus far, what is the cost of refueling infrastructure per kilometer of rail that is there in terms of the model, or if there's some rail companies that have already developed these fueling stations, what has been the cost of the infrastructure for fueling?
The short answer is I don't really know, and it's actually information I tried to source during my research, but maybe understandably, a lot of these companies are keeping what they are doing to themselves rather close to the chest. So it's not directly available, but I think maybe even from the Transnet side, on an operator-to-operator basis, this is something that you might be able to ask from people like Canadian Pacific, and they might be actually freer or more comfortable to release such information to another rail operator as opposed to releasing it in the public. It's very difficult to find such information in the public domain at the moment.
All right. No, thank you for that, Mr. Chitene. That's it on my side. I don't see any questions coming through. Yeah, I also don't see any hands being raised. Links, I think we sense of any further questions. we can close the webinar.
Thank you very much,
Thank you.
Xolani, and thank you for joining us tonight. Ladies and gentlemen, if there's any questions that might pop in now after we close this webinar, we will have it answered by our presenter and mailed it to you. You're welcome to contact the SAIEE Railway Chapter. You would see the email address in the chat box, railwaychapter@saiee.org.za. You can contact them directly and they'll be able to answer your questions or pass it on to Mr. Shintene. And thank you very much for joining us. Have a wonderful evening until the next time we meet. Mr. Shintene, thank you very much for availing the time to talk to our attendees tonight. Have a good evening all. Good night.
Good night and thank you.
Good night.